Welcome to the ZZ training session series. In this session, we are going to introduce the Z simulation and optimization modules used for material characterization. We start with the introduction of the ZMaster GUI menus concerning the Z simulation and optimization modules. As we see on the screen, the ZMaster GUI has various menus like Geom, Mesh, etc. The menu called SimOpt deals with the SimOpt modules. Clicking on the SimOpt menu brings us to the sub-menus of the SimOpt module. Here we see various sub-menu items like var, exp, sim, etc. The purpose of each of these menus will be discussed in detail by using an example. For the material characterization, we will be using experimental data obtained from two trials of tensile tests. As shown here on the screen, the experimental data contains the columns time, strain, force, and stresses. The specimens are strained and the stress responses are recorded in two trials. And for the material model, we use the ZMART generalized elastoviscoplastic model. As seen on the screen, the model uses the isotropic hardening potential characterized by the parameters R0, Q, and P. The Young's modulus is chosen as the slope of the elastic part of the stress strain curve from the experimental data. We start with the material characterization by launching the zmaster command to open the ZZGUI. Here the command is followed by the name of the master file that keeps record of the steps performed using the GUI. Saving the steps performed from the GUI into the master file helps to keep track of the progress and resume work at a later point of time if needed. The name of the master file is arbitrary. The name which we use here is setup.mast. As a first step of material characterization, we load the experimental data. For this, we browse to the SimOpt menu by clicking on it. We then click on the EXP button. This brings up the window shown. In this window, we see various sub-menus. For this tutorial, we will only be using base experiments and related buttons. In order to load the experimental data, we click on the button Add. A new sub-window pops up with the buttons related to loading an experimental database. We browse to the experimental database. And the contents of the loaded database file can be visualized by clicking on the Edit button. Here we see the various data columns of the loaded experimental data such as time, strain, stresses, etc. This window can be closed by clicking on the button Close. The default name of the loaded experiment is base_exp1 and is arbitrary. Now we can click on the button Go to finalize the loading of the experimental database. This adds the loaded data into the list of base experiments. We need to click on the button Close to close the sub-window. We can modify the loaded database by selecting it from the list of base experiments and clicking on the button Mod. This brings back the sub-window. There is a possibility to select the columns of the loaded data to plot them. By default, columns 1 and 2 are selected for the plot. When we click the Plot button, the chosen columns are plotted. The user can change these default columns used for plotting as well. So let's try in this case columns 2 and 5 in order to plot the stress strain curve. As you can see here, the plot is refreshed with the newly selected data columns. Here is an important step where we save the steps done so far. For this, we click the Save option from the File menu. This saves the steps into the setup.mast file. It is advised to repeat this step frequently during the course of material characterization. So the mast file is an ASCII file which contains the ZMaster interface steps saved as a ZZ keywords. Let us visualize this file using an editor. On Linux, we are using VI editor on Windows, you can open it with Notepad, for example. As you can see here, you have many keywords like master, geometry, plotting, SimOpt, etc. And also you have a keyword called experiment, a type of the experiment which is base. We have just added the name of this experiment that we have given as base underscore exp1, and from which file it has been loaded, this database, and the columns which are used for plotting, etc. So the mast file is basically a recording of all the steps performed using the zmaster GUI. Similarly, we add the experimental data from the second tensile test trial database. We can visualize the plots of both the experiments by holding the shift button and selecting both the loaded experiments and clicking plot. So as you can see here, now we have plots, the stress strain plots from both the loaded experimental databases. So as a first step of material characterization, we have successfully loaded the experimental databases into the ZSet using the GUI interface. We now move on to the second step, where we set up the material model used for optimization. For this, we click on the button var, which opens up the sub window shown on the screen with various buttons. As discussed in the beginning of this tutorial, we will be using the generalized elasto-viscoplastic material model with isotropic hardening. And in order to load this material model, we click on the button load from file. And we click on, once we have selected the file, we click on the button go. As you can see here, it has loaded the various parameters of the material model like Young's modulus, Poisson ratio, R0, Q and B into the interface. Here we click on the button switch to panel, which opens another view of the same window. In this view, we can also see the values of the material parameters loaded from the material file. As you can see here, for example, Young's modulus, Poisson ratio, and other parameters like R0, Q and B. The values of these parameters have been loaded from the material file. Here we also see the columns like history items, simulations, and optimizations. The purpose of these windows will be discovered as we progress in this tutorial. Firstly, the history items column shows the list of material parameters that can be saved. For example, we can save the current set of material parameters as initial values. For this, we click on the Add History button and give the name as initial values and click on Go. As you can see here, that this appears now in the list of history items. The purpose of this can be discussed at a later point of time in this tutorial. Before we proceed to the next steps, we would like to save the progress by clicking on the File Save menu button. To illustrate the capability of resuming the optimization module from its previously saved state, we quit the ZMaster window and reopen the window with the saved mast file. So you can reopen. So as you can see here, you have your list of base experiments that you have previously loaded, and also your material definitions and the history item values which you have saved. So in this way, you can actually resume your optimization work each time from its previously saved state. So far, we have loaded the experimental databases and the material model parameters into the interface. The next step would be to set up the simulation. For this, we click on the button Zsim, which opens up the window shown on the screen. We click on the button Add Sim. which brings us to this window. Here we can choose to give a name to the simulation or leave it to be the default value. We next add load block for the simulation by clicking on the button add load block. So we have an error that says that we need to first select a material model. So even before we add a load block, we need to first select a material model for the simulation. So here we can see in this block, the material that we have added in the previous step is already reflecting here. So we can select this and now go to add load block. This opens a tabular window with different fields. For our case, we load it in strain with values similar to the experimental data. So we enter the values of time 2, where we apply a 2% strain. Here the default value for the field segments is 10. This value is the number of data points for the simulation. We will shortly see the effect of this value when we simulate. So after entering the strain value and filling out the tabular column for the load block, you can click on go. And you can see now the block 1 is created here. And to close this window, you can click on cancel. So now you have a load block. So the next step would be to define output of this simulation. So in this case, we would typically want the time, the strain that we apply, and the stress response of the simulation. And when we have selected these fields, you can click on go and then cancel to close this window. And the next step would be to add a plot. And when you click on add plot, you come to this window called define plot, where you can actually choose the references for your simulation. So in this case, you have two base experiments, iterations or trials, where you can add them as references. And then the fields which you would want to compare, in this case, stresses and strains. So you select them and click on go. And here, when you click on go, you can see that a new plot has been created. By the way, you can choose the name that you want to give to the plot, but I leave it to the default value in this case here. And then click on cancel to close this window. So now we have defined a simulation by selecting a material model and then defining a load block and then defining the output of the simulation and then defining also a plot. So having done all these stuff, you can click on the button go, and you can see that now you have a sim1 which appears in the list of simulations. So to close this window, you can actually click on the button cancel. So now we have defined a simulation, sim1. Now you can actually, by clicking on the button mod sim, we can actually get back to the already defined simulation with all the set of parameters. And in fact, you can actually visualize a simulation is nothing but in the background an input file is created. So we can also visualize this input file using the edit file option here, and you can see it opens up a window with the definition of the simulation here. These are all the ZZ keywords like simulate, and here you have a load block, and here the segment of 10, and here you have time, strength, stresses, etc. And here you can see that you apply a 2% strain at a time of 2 seconds, and then you have your material model definition here, and then you also have your output defined. That is, you have asked for a you define the output as time, strain, and stress. So yeah, this is how in the background a simulation file or looks like. So you can cancel this. Now what we can do is we can actually run the simulation, and you can see here in the background that it has run a simulation. And you can also click on plot. So as you can see here, since you have defined your simulation plot to actually show the base experiment curves that you can see here as green and blue, and also your simulation curve that you see here in blue. So this is how your simulation looks like. This is the result of your simulation, the stress strain curve here that you can see. but does not match that of the experimental data. And that's where the optimization comes into play, where you actually try to optimize the parameters of the material model in order to have a simulation result comparable to that of your base experimental data. As we see here on the simulation curve, we see 10 points. This comes from the choice made from the load block definition of the simulation. Since they are very less compared to the experimental data, we can increase it so that we have a better material parameter fitting during the optimization. For this, we click on the Mod Sim button, which brings up this window, and here we choose the load block definition and then click on Mod Load Block. And here, as we can see, we change the segments to, let's say, 50 in this case, and then click on Go, and then you can click on Run. And here you can see that now you have more points in the simulation curve, that is the red line here. Along with the red line, you see also a blue line here in this case with 10 points. So here this option comes from the choice that here it shows two curves for the simulation. So this is basically defined here in the sim plot definition here. You can select the sim plot and go to mod plot. And here by default the history is 2. So in this case, you can, if you can keep it as 2, or you can keep it as 3, or even 1. So what happens here is each time you do a simulation, it not only plots the current plot but also retains the plot from the previous settings. In this case, the previous setting was segments equal to 10. So yeah, that's about it. You can even change it to 3 or 4, even to 1. So it's up to the user's choice. We now move on to the optimization part of the material characterization. For this, we click on the opt button followed by add opt. And now we click on add opt. So this brings up the window shown on the screen. And here the name of the optimization can be chosen or left to be the default value. Also, we have a list of optimization algorithms to choose from. Here we leave it to the default choice, that is Levenberg algorithm. Then we click on the add comp button. So here we choose from the list of simulations on the left column and an experiment from the right. So for a given pair of chosen simulation and experiment, we calibrate the material parameters of the simulation taking the chosen experiment. So the optimization response is quantified with respect to the values chosen from the drop down. So in this case, it is the stress and strain. So having done that, we can click on Go. So here we can see now it has appeared in the list of optimization components. So in our case, we just don't have one base experiment, but we have two base experiments. So we would like to add another component wherein we chose the same simulation but the different base experiment against which we want to calibrate. So we click on Go. So here it brings up this option, this component optimization, second optimization component into the list of components. So here we click on Go. Here it comes up with an error saying that no variable to optimize in optimization item. So we'll get back to this error now, but before that we can see that now we have in the list of optimizations we have opt1 that appears here. So we can close this window by clicking on cancel, and even this one. So in order to fix this error of which says that there are no optimization variable selected, we get back to the var menu by clicking on the button here, and then you can go to switch panel. So in this case, now under the list of simulations, we can see that the sim1 which we have defined appears here, and under the list of optimizations we see the opt1 which we have defined. So here the error tells us that there are no parameters selected for optimization. So here on against each of these variables, you can see there are a list of check boxes. So in this case, in order to optimize, we would want to select these one of these or all of these parameters for optimization. So in this case, we select the R0, Q, and B. We generally don't optimize the Young's modulus of Poisson ratio. So in this case, we have selected these options. And now what happens here is you can actually click on optimize button here. So here we can see that it has given us a set of parameters, optimized parameters. So what happens here in the background is that in the terminal you can see that there are multiple iterations of optimization performed by the algorithm before arriving to the set of optimized values. So here when you click on the button go, these values are reflected in this list. So click on go, you can see that now these values have changed. So now what happens is with these set of new optimized parameters, we would actually want to simulate the simulation. So you click the sim one under the simulation column and then click on simulate. So here now what we can see here is the red curve is the one concerning the simulation, and the blue and green curves are from the base experiments. Now you can see that you have a better representation of the material behavior in terms of stress strain curve from the simulation. So as discussed earlier, you can save the set of parameters of Young's modulus or Poisson ratio R0, Q and B in the list of history items. For this, you can actually click on the add history button and give it a name as optimized values and click on go. So here you can have this. Now what happens here is, in fact, since we have already seen that the simulation curve is very much close to the base experiments with these set of parameters. What we can do is select the initial values from the list of history items and click on load history. This brings back to the list of initial values. So what happens is now you can actually simulate using these initial values. So you can click on simulate and you can see that the red curve, that is the simulation, is what we get with the initial set of values, that is the unoptimized set of values. Whereas the blue curve, that is because of the history, it retains the old curve which is obtained by using the set of optimized parameters. So this brings us to the end of the tutorial. In this tutorial, we have discussed the ZSET simulation and optimization module. We have loaded the experimental data and calibrated the material parameters using a simulator. So for any further queries, you can contact us on the email address shown on the screen. Thank you.